Okay. So we'll try to see if we can get done some stuff which is required towards your homework, which was actually handed out in the previous class, but we could not have the theory behind it on time, so I postponed the deadline for that, so which will be due next Monday. So keeping that in mind, let's first of all review a little bit of the classification, which will help us to set the background for why we need polar coordinates in particular, which will be essential for solving some of the problems that were part of your assignment. In order to understand that, we need to understand how, as far as dynamics in this particular course goes, how we are kind of classifying it. We already looked at some classifications into which we will not go again, which is essentially in terms of the kinematics and the kinetics. So this is essentially about motion, and one is to describe that motion, and the other is about the cause of that motion. So when you're talking about causation, we'll be talking about kinetics, and that's where we'll invoke force, mass, moment of inertia. We'll be invoking the moments, etc. Now, there are other ways in which we are classifying, including the dynamics that we are studying in this particular course, and that is what is relevant, especially for today's class, in which we look at in terms of the dimensionality. So how many spatial dimensions does the problem involve? So typically it could be either 1D, like many of the problems that you solved as part of the previous homework in class. It could be 2D, which is essentially some of the problems that we'll be looking at, especially in your current homework, but also this is something that will revisit us every now and then. Though your many of the books, including what is typically prescribed for this course, tend to bifurcate these in a very rigorous way. We will not be doing that, because in real life problems we will see many of the systems that we'll have to consider will involve a combination of these dimensionalities, and so we need to know how to interface them as well. And finally, of course, this is kind of unusual for an undergraduate course. Most other universities, including MIT, Stanford, etc., do not include this in an undergrad, the first undergrad course on dynamics. But I'm glad Georgia Tech does that, because I think that's what is most appropriate, especially at least for aerospace applications. 3D dynamics becomes very, very critical. So now within this, again, we would have different kinds of possibilities. The simplest case being what we call as motion on a straight line, so which is also called as rectilinear, and it could be on a curved line instead, typically like a curved path that could be, for example, a railway track or whatever. So essentially you're doing that, but still in terms of the description of the motion, it's just one variable which is involved, and which we will typically denote by S and call that as the arc length. So in order to be able to do that, we will arbitrarily specify one particular location as S is equal to 0. So that becomes our reference. Anything before that is negative S, values of S, and positive values of S on the other side. But this is very similar to motion on a straight line, where you would have at some particular point S equal to 0 and S in the increasing direction over here. So there could be certain complications coming because of the change in the direction, because all the quantities that we will be dealing with are vectorial quantities, and even though magnitude may not change of certain quantities, just because of the direction changing, there could be a possibility of certain things being a little more complex in the curved path. but nonetheless both of these come under the category of one-dimensional kind of motion for the, as far as the dynamics is concerned. In all of these problems, whether it's 1D, 2D or 3D, as we already pointed out, it's very, very critical for us to introduce the inertial reference frame, which, as we know, doesn't exist in reality, but we will nonetheless assume that something can be taken to be approximately inertial frame of reference. So what typically happens is that depending, for example, if you're looking at motion on the Earth's surface or even in the Earth's atmosphere, you have an Earth fixed reference frame which you will consider reasonably accurate as inertial. But what happens is that if you are looking for more accuracy, or the numbers involved in the two motions, one is that of the Earth and the other is that of the body with respect to the Earth, in terms of the relative motion and the motion of the Earth, if you compare that, there is a certain level of comparativity, then you might have to move this to the Sun, for example, in our planetary system, and then you take into account body E, on which you fix a frame of reference, knowing that E is not an inertial frame of reference, but you know the motion of E with respect to I, and then you essentially, so this is our, let's say, the Earth, and you have an Earth fixed frame of reference over here, which we will call as E. So for most parts, this itself can be treated as inertial frame of reference, though it is not. But once we are seeing that there is a mismatch in the results, you typically go to a Sun fixed frame of reference, and then there is also a possibility where you might have to move on to let's say if the Sun's motion is also important, essentially a constellation fixed, a zodiac fixed kind of frame of reference as the inertial frame of reference. Nonetheless, whatever it is, none of them are truly speaking inertial, just that what is a reasonable approximation for the problem at hand. So most cases that you encounter in this course, you may not have to deal with this, but it's important to be aware of this possibility of having to move the inertial frame of reference to something which we know is reasonably fixed, in the sense that it's not accelerating or rotating. So this is what is the requirement for this. And once that is done, you have this, and there's also another distinction that you need to make between what all these IE, maybe let's say the Sun, etc. in between, if you want, let me call that as S, and this could be a zodiac fixed reference frame, you could call it Z, but whatever this is, all of these Z, I, S and E are all frames of reference, right? But for each frame of reference, you could have multiple coordinate systems. So there's not a unique coordinate system associated with each of them. You have the liberty in terms of introducing the type of coordinate system. We will see the example of polar coordinates today. You would have, of course, been aware of this from various other mathematics courses, even in high school. The polar coordinate or cylindrical coordinate system, or even spherical coordinate system, and things like that. There are also certain natural coordinate systems that are associated with a particular thing. So we will see that you introduce a frame of reference and then you introduce a coordinate system. So that coordinate system could be Cartesian, which you are most familiar with, the dextral triad of X, Y and Z, or it could be cylindrical, or it could be spherical, or it could be what is called as natural coordinates to a system, which is essentially, once you know the kind of path, you would introduce unit vectors which are tangential to the path, which you will call as ET hat, and those which are normal to the path, which you will call as EN hat. Okay, so this is ET hat, and En hat. So essentially along the entire path you're talking of a tangential unit vector, which of course changes as a function of s in this particular case. Et is a function of s, and your En, which is the normal unit vector to this path. What we have depicted here is of course a planar kind of curves, but it could be a spatial curve as well, something like what you see on some of the rides, for example. It could be a 3D ride where it could have curvatures in both the directions, and you could have, but essentially if you're talking of a 1D problem like this, where there is only one coordinate s that you need to be aware of in order to fix that particular particle of certain mass m, then this becomes much simpler to deal with. But the same thing, whatever we are discussing over here, can be extended to other cases as well. So all this is 3D, Cartesian 3D that we have showed over here. And similarly, your cylindrical coordinate system will be in terms of an r, theta and z. And your spherical coordinate will be in terms of r, theta and phi. And the same thing can be specialized to, these are all 3D, but when you have 2D, all that you do is you drop off the z over here, you just have the xy plane. In this case, in the r, theta, z, you drop off the z and you will have just the r and theta. And in the case of the spherical, you would just have, of course, spherical is you will not use typically, but it could be on the surface, in which case you might drop off r, and you might use theta and phi, which is like on the Earth's surface, it could be the latitude and longitude, if you're not considered about the altitude variations on the terrain. So you could have on a surface as well. So, but then you have to live with what is known as, in such a situation, you would end up with non-Euclidean geometry. So Euclid's kind of geometry is what you learnt as part of geometry in your high school. It's essentially based on certain postulates or axioms that you might be familiar with, but if not, you can go revise that, because that's important. Postulates or axioms, which are essentially based on just a few, it's like 4 or 5, depending upon the fifth postulate. Some people consider it as a postulate, or some people consider it as a theorem. So based on these, assume these postulates or axioms, and then you lead to, this leads to certain theorems that you can prove based on these postulates. So that is your Euclidean geometry, which is valid on a planar surface, for example, but on the Earth's surface, which is curved, or any other curved surface for that matter, when you're trying to deal with, you'll be dealing with certain non-Euclidean concepts as well. So you'll have to make sure you're taking that into account. So we will not explicitly come to that, but where and when necessary for certain problems, we'll introduce certain aspects of this into the problem, so that you know how to deal with such kinds of situations. So 1D, we said that the simplest case is straight lines. The little more complex case is the curved line. Similarly, in the case of 2D, you will have what is known as a planar motion, and you will have a surface or surfacial motion, which is equivalent to having an initial curvature. Just like the difference between a straight line and a curve is that the curve has an initial curvature, whereas here we are talking about the surface, which if it has zero curvature, it is planar, and if it has non-zero curvature, in general, it can be called a surface. So that is 3D and 2D, and here is where you have that possibility of Euclidean or non-Euclidean approaches to the same thing. So this is as far as the dimensionality is concerned. Now, what is the role of the polar coordinates, which we will introduce probably in the second half of this class, is the fact that we will be able to handle some of these curved paths in 1D, the surface in the case of 2D, and some of these more complex 3D surfaces we would be able to handle in a much more easier and compact way. Even though the system itself looks much more complex compared to a simple XYZ Cartesian coordinate system, because all of these are uniform in the sense that they are all length measures. Whereas in an r theta z kind of a combination, you know, r and z are in the length dimensionality, whereas your theta is in radians, or essentially a non-dimensional quantity. It's an angular quantity, and in this case you have two angular quantities, one which is having the dimension of length. So when you have that such differences, some of the things that we will derive, like the velocity and the accelerations, etc., will not be kind of obvious. So we'll have to see what is the novelty that brings, in spite of that complexity of introducing different kinds of coordinates, one or a few, two which are length based, the other angular or non-dimensional. What is the advantage that you're going to get? That will become very clear when we deal with problems related to curved path or surfaces, etc. So then you would see the advantage of that, in spite of the complexity in the derivation of the actual expressions for velocities and accelerations. Right. So I think this kind of maybe one more thing. Another way in which this could be classified is based on how the acceleration is, and this acceleration that you have could be of different types. One is it could be constant, which is what is the kind of motion that you typically analyzed in high school physics, and that constant in turn could be either zero or non-zero, zero being the most simple case where the velocity is a constant. And it could be a variable, examples of which we saw in your assignment that you presented in the last class. So once it is a variable, again, what you considered, most of the examples that you considered were where this acceleration a is a function only of time explicitly. So that's much simpler to deal with, because remember that acceleration is defined as the time derivative of the velocity, dv by dt, which means that you can easily integrate that if you're knowing it as a specific explicit function of t that is given. It could be some constant times t squared, let us say, for example. You know how you could go about integrating that as at cubed by 3, and then you will have the velocity, etc. So it becomes much simpler. But in many real life examples, you will have acceleration, of course, as a function of time explicitly, as you have already encountered before. But in addition to that, it could be a function of the position coordinate, like the arc length, for example. It could also be a function of the velocity, both in terms of magnitude and or direction. So in general, we can call all of these as vectors. Though we will see for 1D problems that we will start with in today's class, the slides, you will see that because it's 1D, you might only the magnitude in that particular direction is of consequence, irrespective of whether it's a straight line or a curved path, and therefore you might just deal with all these as scalar quantities, because you're just dealing with one measure number of that. And measure numbers I've already talked to you about. So for example, if this A is going to be given to you as A along AX along EX hat, and all these hatted quantities are unit vectors unless otherwise mentioned. So AY, EY hat, and AZ, EZ hat. So when you have like this, these three quantities which are, sorry, so these are scalar numbers, AX, AY and AZ. These are the vectors, EX hat, EY hat and EZ hat. So now these three quantities are scalar numbers, and this is what we referred to in an earlier class as the measure numbers. And one way in which you will see a lot of books representing vectors is through a column matrix, in which they would put your measure numbers but it's very important in that case to mention in which coordinate system that is. Because depending upon the coordinate system that we choose, for example, even the same Cartesian coordinate system, I could choose another x2, y2, z2 to be at an angle to this. So therefore, the numbers will change. The actual numbers of ax1, ay1 and az1 will be different from ax2, ay2 and az2. So it's very important that when you say acceleration is this, you also need to specify in which coordinate system, define the coordinate system first and then say this. Because a vector can have various representations, even frame of reference depending upon the choice of coordinates. That's why I wanted to bring in very clearly upfront the distinction between a frame of reference and a coordinate system. Many students initially tend to get confused and think of them as synonymous, but actually they're not synonymous. It's just that you first fix the frame of reference, which is essentially associated with a particular body usually, and then on that frame of reference you choose a particular coordinate system which is of convenience to that particular problem, so that your expressions will turn out to be as simple as you can have. So then the derivations become much easier to do. So this is what we have, and in this case when it was constant, in this particular case, you know that there were very simple expressions, and some of you got confused and started using that. You might use different notations, but essentially it is v is equal to u plus at, s is equal to ut plus 1/2 at squared, v squared equal to u squared plus 2as, etc. Remember that all of these things that we typically use in high school are all valid only under this special case where we are talking of a constant. Okay, so of course it could be a zero or non-zero. So it's essentially, this is the case that for which these are valid, and it's very easy to see that these are all just integration forms of the definition for your acceleration and your velocity. Is dv by dt, and here you're taking typically this so-called rectilinear motion. This rectilinear motion is where you can deal with, even though knowing fully well that these are vector quantities, because they're all on a particular straight line or a curved path, you can just treat them as scalar quantities, which is what we will see shortly in the slides. So in the beginning part of today's class, so where you will just have a is equal to dv by dt, and if a is a constant, it's very clear to see that this is going to, if you integrate this, you would get integral dv is equal to integral a dt between some time t1 and t2, and essentially v1 and v2, which we are calling as u and v in this notation that you are familiar with. Sometimes I think s is written as d, the distance. S is actually the arc length, which is equivalent, just two different names for the same quantity. So when you have something like this, it could also be t1 equal to 0, and you just call t2 as some time t over there. So then you see if a is a constant, it just comes out of the integral, this just becomes a into t, the other limit of course being 0, so therefore that minus 0 becomes just at, and on this side you have v minus u, and you see that this is what has led to your equation that you have probably used quite a few times in terms of solving a lot of problems. So then of course you would have the second definition of v is equal to ds by dt. Now you would just substitute this v is equal to u plus at into this, and then integrate this in order to get your, if you integrate this on both the sides in this using the limits like what we did, we end up with this particular equation that you see here. We start with s is equal to 0 to start with, at t equal to 0. You're defining, we talked about a certain benchmark or a reference that you have to start with. So you would typically say, let's say s equal to 0, t equal to 0, then essentially that's where you're ending up with is s is equal to ut plus half at squared. So very clearly, we use the definition of acceleration to get the first equation, the definition of velocity to get to the second equation. What do you think we need to use to get to the third equation? Come again?
The first equation
Yeah.
looks very similar to it, but I don't think it is.
It is not, because this involves a time, this involves a distance. So that's the difference. The rest of the quantities are the same, V, U, and A. So essentially you are trying to relate these quantities V, U, A, S, and T. So there are totally 5 variables. Okay, and you're typically given some of them, and you try to determine the rest. Yes, so that.
This is for yes, but could we possibly take the first equation, use the second equation to solve?
Can you, do you want to try? Yeah, yeah. So first equation, in the sense you're taking this, right? And you want to
plug in the t from the second equation, like solve for t.
Good. Yeah. Precisely. Yeah. So you see, because essentially you want a relation between V, U, A, and S, which is what I was trying to get over here. So which means that if you want a relation between these, which is a subset of the 5, then you have to eliminate t. Okay, so you have 2 equations in which both of which you have t. So you essentially substitute for t from one into the other, and you get that. You could also do the same thing using the differential equations as well. So you can write your A as dv by dt, which can be written once again, instead of dv by dt, I can put it as the right hand side of that as dv by ds into ds by dt. Okay, so essentially I'm multiplying and dividing by ds. So then I can have this ds by dt as v, right? So once I have ds by dt as v, this becomes v dv by ds, and the other side it becomes a ds, and then I integrate. So once again I'll end up with this, just that you have v dv, so that will lead to a square. So that's where the limits of that square at t equal to 0 and some arbitrary time t become u squared and v squared respectively, and you end up with this, and the right hand side becomes as. But then you also get, when you're integrating v dv, you get half, because it's v dv, so you get v squared by 2. So that 2 goes on the other side, which is how this particular 2 comes. So one is entirely through the definition of acceleration and velocity through the derivatives of the velocity and distance respectively, or as Siddharth pointed out, just by eliminating t out of the first 2 equations. In other words, these 3 equations are not independent of each other, so you can try to get that. Very clear to see that there is a t squared involved, which is why you will end up with squares in terms of v squared and u squared when you eliminate that. Okay. So the reason why I'm kind of bringing this, some parts of this high school physics, is to show that this is not like you forget that knowledge and you get to something else. It's all a part and parcel of what we are looking at. Acceleration in general can be any function of time. In fact, it can even be functions not only of time but also s and v. But of course, in turn, s and v are functions of time. So once you solve the problem, you might be able to express acceleration just as a function of time. But usually, combinations of the displacement rather, the velocity and the acceleration are sometimes not known, which means that right hand side cannot be explicitly obtained in terms of t in this most general case. So it is very much possible that you might have to deal with this, and their integration becomes very, very complicated, if at all possible. And so there we will see some examples of that and how to deal with those specific cases. But what we are saying is that if as a special case of that is where A is a function only of t, and a special case of that is where A is a constant. Right? Constant is also a function of time, just that it doesn't change with time. Yeah.
For the equation you have up there, a equals dv dt, integral dv j, and then integral of a dt, and then you do v minus u equals a t.
Yeah.
Right? So that's for constant acceleration.
Exactly. All of these are for constant acceleration.
But
Yeah.
since velocity is still going to be the integral of acceleration, can you instead, like for that a dt, integral of a dt, replace a, if it's not a constant, just a, can you just replace it as whatever function it is?
Absolutely, yeah. So when you have this kind of a problem, that's what you're going to do. And in fact, you already did that as part of the homework without explicitly knowing about it. But for example, when A is the acceleration is like a t squared dependency, is proportional to t squared. For example, that's what you'll be substituting here. You get t cubed by 3, and then you substitute the limit. So these definitions, that is the fact that acceleration is dv by dt and the velocity is ds by dt, these remain all this same all the time. Just that, of course, here we are talking about rectilinear motion, so we are taking a, v, and s as scalar quantities, which is luxury that you will not have very often. So you will have to take a, v, and s as vectors, and which means that you might also have to specify with respect to which frame you're taking the derivative. If there are multiple frames, many times textbooks might ignore that because there might be only one frame that becomes the default frame, and anyway that all derivatives are with respect to that frame. But it's important to keep that in mind, that frame is important for derivatives of vectors. So that's essentially what it is. It's a very good question that brought about that while the boxed equation on the top is not valid for the cases where acceleration is not a constant, these two are still valid for all cases in general case, and these can be used in the exact same way that we have used over here in order to integrate in one case the acceleration, integrate the other case the velocity, and even v dv, this kind of a breakup of dv by dt as dv by ds into ds by dt. That's something that you can do in the general case as well, just that you have to be clear that when you're integrating, you take the actual functionality into picture. So I think things are clear over here, right? So are there any issues? Okay, good. One more equation which is probably used quite often is in terms of the average speed, because it's a constant acceleration. So you know that v is linear function of time. So if it's a constant acceleration, you know that for this case, if you plot v of t versus t, these diagrams are very important many a times. So you would see that at t equal to 0, the velocity is u, and at some time t, it is v over there. So you can think of the average velocity during the duration of your interest, which is only between 0 and t, as v plus u by 2, right? So that becomes your average speed. V average is equal to v plus u by 2. This is only in the case of constant acceleration, and then you can multiply that velocity by the time, you will get the distance. So that is another way of putting it. S is equal to v plus u by 2 times t. So that you could add one more equation to this, saying that v plus u by 2 times t is equal to your s. Okay, so this is also something that you would have used quite often in your school physics, but once again, it's valid, even though acceleration might not explicitly appear in that, compared to these three equations where a is there here, a is here, a is here, over here. There's no a in the first equation, but that is valid if and only if acceleration is a constant, even though acceleration itself doesn't appear in that equation. Yes, Siddharth.
When we're talking and when we're putting this into non-constant acceleration, could you also find the average by taking the integral and dividing it?
Absolutely, yeah.
And then can we use that same equation?
Yes, and It's no, see, what you're having is an arbitrary function like this, okay, of velocity with respect to time, and the area that you are having is essentially integral v dt, right? So which is essentially what you would have from this v dt is equal to ds. So your ds would be an integration of that. So this is essentially your VDT integral from, let's say, 0 to some time t, and your VDT is nothing but ds, right? So when you're integrating, you will get s at t and s at 0. So you would get the change in distance that you have. Yeah, you would be able to do that. Yeah. See, always remember that these are the equations that are always valid. Your A is equal to dV by dt, and V is equal to ds by dt. And you can, of course, manipulate it in different ways. So irrespective of what function A might be, you would be, if at all you are able to integrate or plot, then you can take advantage of that. So always a VT curve, the area under that would be distance, because of the fact that you have V and T over here and S. Similarly, in an AT curve, always the you would get the difference in velocity from the final point in time to the initial point in time.
Yeah, the reason I brought it up is
Yeah.
because in the previous question we didn't do this, but the time was changed from reference. The reference frame changed like the time period that we're going. So if you're multiplying by delta t, it has to be based off the reference frame.
Yeah, yeah, of course, of course. So you can't change in between, let's say at some t in between, some t star in between 0 and t. If you're changing the reference frame and the data you're plotting is for the changed reference frame or a changed coordinate system, then this would not be valid. You will have to have some consistency in terms of how you describe that, and appropriately you will have all the results mapped onto that particular frame of reference and or coordinate system. See, the vector itself is immune to the choice of coordinate system. It's only when you put it in some specific form like this as measure numbers, etc., then it becomes dependent on the coordinate system. Otherwise, A itself is not coordinate dependent. Okay, so A is a vector, and then when you want to express it in a particular system, you dot it with the unit vectors of that system. You will dot it with Ex hat, Ey hat, and Ez hat in order to get your Ax, Ay, and Az. Then it becomes a specific value. Now this is not universally valid, it's valid only for that coordinate system. But A itself is universally valid. Okay?
So it depends on what you're taking, the unit vector.
Yeah, yeah. So this is, as soon as I have put it in this form or this form, they are equivalent to each other. So I have already put it in a particular way. Now I can write the same thing as equal to ax1, ex1, ay1, ey1, ay2, ez2. Both those are equal to each other. Okay, so the sum is equal to each other. Just that the individual terms will become different. So, and each of these, again, I'm beating the drum, but it's important to recollect that these are measure numbers, whereas each term along with the unit vector becomes a component. So this is the x component, y component, and z component. The components are all vectors, whereas measure numbers are numbers and therefore scalars. Okay.
So, but the components are
Yeah.
are they since they're vectors, they're also fine in any, they're all the same in a different reference frame or no?
Very interesting point. See, you're essentially putting a vector as a sum of three vectors, and each vector by itself is independent of the coordinate system. But you will have to, of course, then express that in that particular system in order to get its measure numbers or components in a new system. Right. But what you're saying is absolutely right. It's a property of vectors that a vector is immune to the coordinate system. And even when I break a vector into three vectors, each one of those is a vector, and each one of them will follow that property. Okay. So there's no doubt about that. Just that when you to actually deal with it or manipulate it or use it in a derivation, etc., you will need the actual expressions for in the particular coordinate system of choice. Okay, so you might use the same system for expressing that or a different system, doesn't matter. Vector itself doesn't change, but its measure numbers will change. For example, if you use the same system, then just it's quite obvious that it's a trivial thing that it just becomes these. So for this vector over here, just the first term over here is a vector, will have a component ax 0 0. Similarly, the second one will have 0 ay 0, and the third one will be 0 0 az.
And those measure numbers are not in the
Correct, because the measure numbers will depend on how you are expanding each one of that. Even though I have expanded A in the Ex hat, Ey hat, Ez hat system, I might choose to expand this first vector in a different set of unit vectors. I have the freedom to do that. And then of course it will be different in general. Yeah, so I think this is what I wanted to convey before we get onto the slides. Is this clear? Anybody, any other questions? Let's go. Yeah, now you might want to switch off the lights, Kush. Is the visibility okay, or should I close the door as well? Prefer to close the door?
You guys see it?
You can see it, right? Shall too? Yeah, okay. So this is just an extension of what we did with the scalar functions to vector functions. So it's quite obvious. So all that we are saying is that when we have different kinds of combinations of vectors, one is it could be a sum of two, one vector is defined as sum of two vectors. Other case it is defined as a product of a scalar quantity times a vector. In the third case it is defined as a dot product of two vectors leading to a scalar function, of course. And each of them is a function of time. So in general, both the left hand side and right hand side are functions of time. And the last case where you have a cross product instead of a dot product, where it left hand side remains a vector, which we call as v of t. So now these are the four things that you will very commonly encounter in dynamics class, where and are very basic to linear algebra or vector algebra that you would have probably encountered in many different contexts in other courses. So the thing is that we saw in last Thursday's class very similar set of four quantities where the right hand side quantities were all scalar quantities, and then we said that if you want to take the derivative of the left hand side, what happens to the right hand side. So that is essentially what we did. Same thing, we are just extending that to the case of vectors over here. And it goes without saying, very easy to prove these from the very definition, because remember that the derivative we define in terms of a limit of the numerator and the denominator, with the differences that we are talking about in the quantities essentially going to 0 as far as the denominator is concerned, and therefore what is the ratio of the numerator to denominator. That is in terms of the limit that we define, and from that definition it will be very clear that if a vector is a sum of two vectors, then its derivative is also sum of the derivatives of those two vectors. So in other words, either you can sum first and then take the derivative, or you can take the derivatives first and then take the sum. So that's all that this means. The second thing is where a vector is defined as a product of a scalar function and a vector function. In the previous class on last Thursday rather, we looked at only scalars, and today we are primarily looking at vectors. But here is a combination of a scalar and a vector. But whatever any two quantities, if you are defining a particular quantity as a product of those two quantities, then you have a form like u times v, which becomes u dv plus v du if you want to take. So which is essentially what we are talking about here. You have two quantities whose product you are interested in, and you are essentially taking the derivative of one at a time and keeping the other the same. So you keep f the same, take the derivative of u. Here you keep u the same and take the derivative of f. So in this case, it doesn't matter as far as the order of these is concerned, but in some cases you will see that the order matters. So it is important that you keep the order the same just for consistency, then you will see that everything works fine. The third case is where the dot product of two vectors, vector functions leading to a scalar function, and when you have that, once again the udv plus vdu works. Once again you take the first vector as it is, the second vector you're taking the derivative with respect to time, then you're taking the first vector's derivative with respect to time multiplying by the second vector. And multiplying is very, very important to be very precise in the case of vectors, whereas here I didn't need to say what kind of multiplication it is between a scalar and a vector. It's just an amplification that this does for that vector. In other words, it changes its magnitude, whatever its I'll come to you. It changes its magnitude by a certain factor. So that factor, if it is smaller than 1, it essentially shrinks it. If that factor is larger than 1 for given time, then it kind of amplifies that vector. Yes, Kush.
Oh, isn't that like a product of an actual like function of time? So how is that a scalar in this case? Like
What is, see, f of t is, you're talking of this?
no, the one above.
Okay, yeah.
How is it a scalar if it's a function of time?
You can have scalar functions of time, right? Like for example, sine x is a scalar quantity. If x is a scalar quantity, sine x is a scalar quantity, right?
Yeah.
So it's some function of that, right? So by scalar, what we mean is that just by specifying its magnitude, we are done. We don't need to specify its direction.
Oh, okay.
So that's all that it means, right? So any function which is essentially written without the arrow, or some cases it's a bold notation or a hat notation for unit vectors, etc. So this is essentially talking about a scalar quantity. The underlying assumption is that we know that convention, that notation without a bold, without a overbar or underbar or a hat, essentially we are talking about a scalar quantity whose only magnitude matters. There's no direction associated with it. So it could be, for example, pressure, it could be, for example, temperature, it could be mass density of a particular material, etc. These are all examples of scalar functions, and those could in general change with time. Yeah. Is that clear? So yeah, we were talking about this multiplication of two vectors. You have to be very, very precise. Whereas here, multiplication of a scalar with a vector, we didn't need to qualify that with something else, an adjective. Here we need to qualify the product as either a dot product or a cross product. And that's what remains in terms of what the left hand side becomes. Once it's a dot product, it's also called as typically a scalar product, which is why I didn't write this as a scalar product, because this is a product with the scalar. Okay, product with the scalar is different from a scalar product. Scalar product is another terminology which is used for dot products, where you have dot two vectors and then you essentially end up with f of t. So you know, you've probably solved a lot of problems like that. So you dot a with let's say v, you are going to get ax vx plus ay vy plus az vz. So that's essentially what it is, and you can see only magnitude there matters at the end, not the direction, and therefore you end up with a scalar quantity, scalar quantity over there, which you're calling as f of t over here. So when you have something like that, once again that udv plus vdu continues, and therefore you maintain the order. First term should be v1s, second term should be v2s, with or without the dots. So one at a time you take the dots. So here you've taken dot with v2 first, and then kept v1 as it is. Here you've taken the dot with v1 and kept v2 as it is. So that's what you're trying to do, and you end up with this scalar quantity f dot of t. Yes.
Would you take the derivative of each component and multiply that?
Yeah. So good point. So essentially, how you carry it out in terms of the actual numerics, that's precisely what you would do. Like for example, this would involve v1x, v2x plus v2y, v2z, v3y, v1x, v2x plus v1y, v2y plus v1z, v2z. Okay, so that's a scalar quantity, and you will for each one of those terms you would take derivative of the in any u into v. You are taking the derivative of u, then multiplying by v, and then taking u and taking the derivative of v, right? So to actually carry it out term by term, that's what you would do, but this still remains valid as a vector equation. So either you can First take the dot of the vector as a whole and then dot it with this, or you can dot the two vectors, get scalar quantities, and then you can use the equations that we discussed last Thursday, which was just a product of two scalar quantities. You know how to take the derivative of that. So both are equivalent ways of doing it, right? So this is what we have over here, and finally where the left hand side remains a vector, because the kind of product that we have now is the cross product. I think you're all familiar with the cross product, right? So for example, if your unit vector system is Ex hat, Ey hat, Ej, Ez hat, you would have a determinant where that is the first row, Ex hat, Ey hat and Ez hat, and the two quantities whose cross you're taking will be the second and third row. Their measure numbers will be the second and third row. So that you will have V1, maybe this. So your So the determinant of that is what we're talking about over here. So it remains a vector. So when you're trying to take the derivative of such a vector, which is defined as the cross product of two vectors, you will see that once again the udv plus vdu works, that you take derivative of one of those terms at a time, keeping the other the same. So you keep V1 the same, take the time derivative of V2. You keep V2 the same, take the time derivative of V1. And here where it's very important to keep the order. You can't interchange, you can't put V2 over here and V1 over here. You will get the negative of that. So because A cross B is negative of B cross A in general. So unless it's 0, in which case both become 0 and therefore equal. Otherwise they're not equal to each other. So essentially what you're doing is you're interchanging the second and third rows. And you know, in a determinant operation, when you interchange any two rows, you're going to end up with a negative value for the same determinant. So that's essentially what will happen. So whereas here it doesn't matter. If you're going to interchange V2 and V1, the dot product doesn't change. Or if you're going to have a scalar quantity multiplying a vector, if you interchange, the order doesn't matter. But here it does matter. So it's good to be consistent all through in terms of keeping the order so that you never go wrong, right? So that's essentially what we do. And then these two, the sum and product with scalar in dynamics, we will see as we go through in the future classes, we'll use these two equations quite a bit. Once in a while we'll be using these equations as well. So it's good to kind of remember that, but it's just an extension of this scalar quantity definitions that we introduced in the last Thursday's class. So yeah, so we'll see why that is the case in the next slide. Is this clear? Any doubts on this? Yeah. Okay. Now, in terms of the derivatives, because we had quite a few derivatives in the previous slide, if you look at, there were lots of time derivatives of the vectors. So we should know how these time derivatives need to be calculated, right? So that's essentially what we are looking at over here. And I mentioned this in passing in one of the earliest classes as well as part of this course. We had said that there are many quantities of importance when you're taking the derivative of a vector. So vectors are typically represented in terms of the measure numbers, like what we did over here. So a particular vector is defined in a particular set of measure numbers once the coordinate system is fixed. So once you do this, it becomes, let's say the choice of the coordinates is x, y, z, and the corresponding unit vectors are I hat, j hat, and k hat. Then you have the measure numbers along that, vx of t, vy of t, and vz of t respectively. So it becomes the sum of those three, right? Now, if you're talking of taking a derivative of this vector v of t with respect to t, then there are quite a few things of that you need to keep in mind. One is the reference frame. First of all, you already chose a reference frame and a coordinate system associated with it to express the vector. But in addition to that, you also need a reference frame with respect to which you're going to take the derivative. So, of course, the quantity with respect to which you're going to take the derivative is t, which is what is going to lead to your v dot of t, right? But that alone is not sufficient to tell that I'm taking the derivative. You also need to say with respect to which frame of reference. So, you need a reference frame, which we will abbreviate as FOR, frame of reference. Then you also need a coordinate system like what you have already taken into account, the IJK, and therefore the XYZ coordinate system, along with you have the measure numbers. The third thing is, of course, the unit vector itself, that is I, J and K that are there. So whenever you need to take a derivative, you need to ensure that all of these are clearly defined, because if somebody else defines some other way, it's very much possible they get a different answer and we are comparing. Both might be right, but numerically you might have different measure numbers, but that's fine.
When you take the derivative, you see the original frame of reference, it stays the same, right? Or no?
It depends on with respect to which frame you're taking the derivative. You might define with respect to one particular frame in terms of expanding. If you're taking the derivative with respect to the same frame of reference, then your I, J, K will not change. So then only you need to be bothered about these being functions of time. Okay, in general I should write this, that I hat is a function of time, J hat is a function of time, K hat is also a function of time.
I, J, K hat, they're different than the one in the next one?
Yeah. So this is the more general thing. I'm just saying that this is a special case which is possible only when you have the same frame of reference chosen for expanding and for taking the derivative of this. So in other words, two frames of reference are associated with any vector derivative. One frame of reference where you expand the vector, another frame of reference wherein you take the derivative with respect to. So both are important and both need not be the same all the time. Okay. So if they are the same, things become very simple. You don't need to take derivatives of the unit vectors, you need to take only the derivatives of the measure numbers and you're done with it, right? So that's essentially what you're talking about over here. So now we come to a more generic case where you have different frame of reference with respect to which you're taking the time derivative, in which case you'll not only have the Vx dot, Vy dot and Vz dot terms, but you will also have the I hat, the dots of the unit vectors that are there as well. So you can see your I hat dot over here, J hat dot and K hat dot over here. And what we are using is one of the rules that we introduced in the previous slide, where we are taking the product. If you're taking this product, you take derivative of one and keep the other the same. Then you take this as the same and take the time derivative of the other. So it's only when you're taking the time derivative of this, you have to be careful with respect to what you're taking. Now, it's very clear that if I'm taking the time derivative with respect to the IJK frame itself, then it's clear that the dot will be 0. So these even terms, the second, fourth and sixth, will all go to 0. So you'll have just the first, third and fifth terms. Whereas if you're choosing the dot with respect to another frame, let's say LMN, L hat, M hat and N hat, then these in general can be non-zero quantities and you'll have those three terms contributing as well. Yeah. So next, first of all, many people get confused. Can unit vectors at all change? Yes. For example, we were talking about, let's say, a zodiac fixed frame. We had a sun fixed frame and an earth fixed frame, and an aircraft or even a surface vehicle like a train, etc., moving on the earth. You are trying to monitor that with respect to the earth. Then if you're taking the derivative with respect to a relatively closer inertial frame quantity rather than E, then you will see that E is also going to move with respect to that, and you'll have to take that into account. So you might expand the aircraft's motion along the coordinate system that is fixed to a reference frame, which in turn is fixed to the earth, an E fixed reference frame, but the derivative might be taken with respect to a sun fixed reference frame, which means that the motion of E in S, that is the earth in the sun fixed reference frame, will also need to be taken into account, and that's how those additional terms come into picture. So can unit vectors change? Yes, they can. So that's an example of that. So that's why your frames of reference as well as the coordinate system are very, very critical. You have to define them upfront. Any problem that you get before you start solving the problem, always do this exercise of fixing the frame of reference on the choice with respect to which you're going to define other quantities. On that, introduce a coordinate system. They are two different things. Remember, frame of reference is different. The coordinate system is different. Both have to be introduced upfront, and you make an argument as to why that is a reasonably good approximation for an inertial frame of reference, and therefore your most of the laws that you're aware of motion, the laws of motion are valid, and then you will go ahead and implement them, right? So next, the inertial frame of reference with Cartesian coordinates is the easiest to differentiate. So like the one that we introduced over here, the x, y, z system over here, rather than an r theta z or the r theta phi, the polar, cylindrical or spherical coordinate systems. Compared to them, this is something that is usually much easier to differentiate, because in these cases you will see that those the hat quantities, instead of ex hat, ey hat, ez hat, you will now have er hat. In the cylindrical coordinate system, for example, you will have er hat, e theta hat, and ez hat. Okay. Now, er and e theta hats can change with respect to time, because if theta changes with respect to time, because at different thetas you will have the radial direction changing, you will have the tangential direction changing, and therefore you will see very easily that they are functions of time. Whereas something like this, they're not functions of time over here, unless of course the body to which they are fixed, that frame of reference itself, is moving. All right. So that's why frames of reference are important. The coordinate system is important as well. The inertial frame of reference, or what we abbreviate as I4, with Cartesian coordinates is easiest to differentiate. But then that's not the only thing we'll be exploring in this course, because even though it may not be easy to differentiate, sometimes using these kinds of coordinate systems, the cylindrical and spherical, etc., or the one that I talked about, the natural, which is involving tangential, normal, and we will introduce a concept of binormal, which is a cross product of the tangential and the normal. So we will have another kind of set of unit vectors which we will use quite often. So it's important that for the specific problem, depending upon the geometry of the motion, one might be more compact and convenient and easy to utilize and make derivations out of compared to the other, even if it is non-Cartesian. So that's something that you need to be aware of. So non-inertial frames of reference, that's what the last bullet point over here says, that and or non-Cartesian coordinates. See, again, this could be a combination. You could have an inertial frame with Cartesian, you could have a non-inertial frame with Cartesian. Similarly, you could have an inertial frame with non-Cartesian and a non-inertial frame with a non-Cartesian. So all of these possibilities are there, and you make the choice. That's one of the important things that we do at any dynamics problem, is to make the choice which is convenient or most conducive for that particular problem, so that your derivations can be done very compactly. But what if somebody else chooses a different frame or a different coordinate system? The final answer, when it's referred to a particular coordinate system, should all be the same. It really doesn't matter. These are kind of your intermediate steps, or your choices of, you have to be, throughout your derivation, you have to be consistent with that. As long as you're consistent, your end result, when expressed in a particular frame of reference, all of your answers will all match with each other if all of you have done it appropriately. So there's no hard and fast rule as to you have to choose this particular coordinate system or that particular coordinate system for a particular problem. Just that the choice you make can make your life difficult or easy. So just that the derivations will be much, much simpler with a particular system. So make certain problems easier to solve overall. But as I said, non-Cartesian frames, usually you will have the differentiation very, very complicated. as we shall see some examples today. So now we come to this particular thing that we talked about over here, the straight line motion, rectilinear. So which is the simplest case of dynamics that you could have, where everything is moving on a straight line, and therefore you don't need to deal with vectors. You can just deal with scalar quantities of magnitudes of those vectors, right? So consider the motion in a straight line like this. If you're analyzing just only one vector measure number. So in other words, along that line, if I define that as the x-axis, so or Ex hat is along that, very clearly would have only the x component of all the quantities, Ay, Az, Vy, Vz, Sy, Sz will all be equal to 0. I'm only dealing with Ax for acceleration, Vx for velocity, and Sx for the displacement, which means that I can just deal with scalar quantities and be done with it, much simpler to handle, right? So the position vector in that case, instead of S, we typically use a position vector R. So let me just erase this. So you have all the motion is taking place on this line. You have defined S equal to 0 over here, and some S of t at some other point. Okay. So now when you're talking about this, now you have to first of all introduce a particular reference frame. Let's call this as I, and then you have introducing, let's say, let me just, the reason why we are calling this as Ex hat, Ey hat, and Ez hat is that it is fixed to a reference frame E. So this is a convention we typically use, that we use the uppercase to refer to a frame of reference, and these quantities to refer to the unit vectors. So we use the same letter. If you use uppercase E here, we use the lowercase e to refer to this. So similarly, if you use an aircraft fixed frame of reference in which we want to see how the rotor blades in the turbine or compressor are moving, we might call another frame A, and we will introduce Ax hat, Ay hat, and Az hat. So small letters A, so that we know that 1:1 correspondence between a particular frame of reference and the corresponding unit vectors. But as I said, you can have multiple coordinate systems associated with the same frame of reference, in which case of course you will have different notations for that. But wherever it is a single coordinate system associated with a particular frame of reference, you use this correspondence, that you use uppercase for the frame and lowercase for the unit vectors associated with that frame. Right. So when you have this, so the first quantity you're talking about over here is this position vector R of t. So now in a general motion, this would be at some point you would have this as the position vector R of t, right? But for this simple problem where everything is moving on a straight line, you might as well move the origin to this particular point. Instead of having it over here, you can move this origin over there, and you can align your Ex hat to be along this. So in other words, you could put your Ex hat along this, and it doesn't really matter the Ey hat and Ez hat over there. So you're starting with O over here, and therefore your position vector, which you are drawing from some arbitrary origin far away, now becomes from this particular O, and therefore it just becomes at any given point, it becomes the magnitude, which is nothing but S of t, times the unit vector, which is Ex hat. So your R just becomes your S of t times Ex hat in this particular case, right? Clear? So that's as far as the position vector is concerned. But now, as I said, we don't even need to deal with vectors. So, and therefore, no need for unit vectors either. So we don't need to have this r of t as a vector because we are interested only in its magnitude. So that's why what we have written over here as r of t without a bold or an underline or a arrow on top means that it is a square, even though I'm calling it a position vector, I'm not talking of the position vector itself, but its measure number. So its measure number along the straight line in which we are considering the motion, and therefore we are looking at r of t over here. So then the velocity measure number would therefore be a time derivative of this, which will just be v of t, again a scalar quantity because it has only the x component. It's essentially vx of t if you're looking at from a vector point of view. And similarly ax of t, we're just calling it as a of t. So they just become three scalar quantities. Now the equations, coming to the equations, once again it's the vector derivatives that we are talking about with respect to time, but now all those vectors have only the x component, and therefore we are just dealing with the value of that component. So the magnitude of the velocity as a function of time is equal to the time derivative of the position vector with respect to time, right? So now we are talking of only the measure numbers rather than the vector itself. Similarly, the acceleration is v dot of t, that is also quite clear, and which in turn, if you substitute this r dot of t into the second equation, you're going to get r double dot of t, which is dou squared or d squared r by dt squared, because it's only one independent variable. You don't even need partial derivatives. Ordinary derivatives are good enough. So is this clear? Yeah. So next, so the simplest kind of examples would be when the quantity whose derivatives are defined as some other quantity. So that all that you need to do get to the unknown quantities is to take the derivative of the known quantities. So for example, if I'm given the position vector, or rather let me not call it as position vector, but the measure number of the position vector, because it's a rectilinear motion. So I'm just given r of t, then very easily from the previous slide we know that we can get v of t as r dot and a of t as r double dot. So I'm able to find the other quantities of interest. So this is all that most of your dynamics problems will be. Some combination of r, v and t are given to you, and some certain things are unknown, and so you're going to use more generalized forms of these. These equations which you used in high school physics were valid only for a equal to constant. Now for a not equal to constant, how do you go about doing that? So it's essentially integrations. But problems like these where r is given and then v and a are asked for, or if just v is given and a is asked for, where all that you need to do is to take a derivative, are going to be rare. Those are the simplest kind of problems that you can encounter in dynamics, and that's a very, very easy analysis to do. You'll just be differentiating. But in most dynamic problems, you would encounter integrations, because you might be given one of these quantities and asked to find the position or to find the velocity, or rather the speed, because we're talking of rectilinear motion over here, and that involves integration, which is usually a little more difficult. But even the integration can be easy if erase those things. But we were talking about different ways of looking at dynamics. One case where A is function only of time, not of velocity and the displacement. In that case, again, even integration is not all that difficult, especially when you have the integral calculator at your hand. So it becomes very simple. There you're doing the reverse. You're given A, you find V by one integration. One more integration, a double integration with respect to time, you end up with R of t. But each stage you'll have to apply appropriate conditions in order to go to the final result, right? Next, a simpler problem would be when velocity is already given to you as a function of time. Again, it's not appropriate to call it velocity. Either I have to call it a measure number of velocity or a speed, because we're talking of rectilinear motion. It's not a vector, it's a scalar quantity. So given the speed as a function of time in rectilinear motion, I can get the displacement, or more appropriately the distance or arc length as a function of time, which is essentially giving you the position as a function of time. So then there are four, each one of these columns represent four different ways of solving the same thing. They're all one and the same essentially. It involves the integration process, but you're defining it in a different way. One is using definite integrals, the other is using indefinite integrals. The third is essentially both the third and fourth are initial value problems, but the third involves first order ordinary differential equations, but a system of them. And the second one involves involves a single one, and here you're talking of a second order differential equation where you have a single quantity that you have to deal with. Here you have multiple quantities, so you have a system of equations that you have to deal with. The order will be lesser, but instead of a single variable r that you're dealing with two variables r and v over here. So let's go with them one by one. So all of these are of course following from the definitions that we have over here, namely A is equal to dv by dt over here, and v is equal to ds by dt over here. So these two are what we are trying to integrate, and that's essentially what is happening. So the definition of acceleration as dv by dt, you're just taking the dt to the other right hand side, and you're integrating from initial time 0 to arbitrary time t, and then you get on the right hand side v, but of course you have to apply the same limits on that side as well, which becomes v of t minus v at 0, right? So all of these are scalar quantities. We're still dealing with rectilinear motion. We will generalize it to the more generic motion later on. Now one more integration of this. Once you have got the v of t over here, you put substitute that v of t into this integral, and you take this particular definition that you have. So v is equal to ds by dt is the definition of velocity, and this is the definition of acceleration. So from the definition of the velocity, or the speed rather in this case, you get the position. If you know the position at time equal to 0, you get the position at some other time. So this is using definite integrals, because you have the limits specified over here. You have the definite integral approach to solving the problem. Next, you have the indefinite integral approaching the problem. You just have the integral without the limits, but you will introduce a constant of integration. So you introduce one constant of integration at the first integral when you're getting the speed as a function of the acceleration. Then you're going to then get, eventually you're going to get the position as a function of time, which in turn is by integrating the speed as a function of time, you get the second constant of integration over there. And how do you calculate these constants of integration? By applying the initial conditions. The initial condition in this case is the initial speed, and in this it is the initial position. Usually this might be taken as the reference 0, but it could depend on the convenience that of the particular solution. Yes.
And this can be translated to like rotational.
Absolutely, yeah. It's just the choice of coordinates. So instead of x, y, z, you're going to have that system, right? So r theta z if it's a 3D motion, but for 2D motion, you're just going to have r theta instead of x, y. Yeah. But you just have to make sure that in the case of your ijk, they were all not functions of time. But you know er and e theta are going to be functions of theta, and if theta is a function of time, they are going to be functions of time as well, right? So in other words, you have this curve, right? Part of a circular arc that you have. This is the origin that you're talking about. This is the vector that you have. So this is the position vector that we've been talking about, r.
Like angular velocity equals the integral of angular acceleration.
Yeah. See, whatever I'm talking about here is valid only for rectilinear motion, right? It's just a straight line that we are talking about, okay? So this is a much more complicated problem where you have at least 2D motion, okay? At least two coordinates are involved. So there it's only one coordinate which is involved, which is required over there, yeah? So here when you're talking of a position vector r, at some point wherever that particular let's say particle of certain mass has gone, it is at a particular location at some time t, that r is going to be a function of time t, right? So now your unit vectors are going to be along the normal, so that is your ER hat, and it's going to be tangential, which is ET hat over there, right? Now you see that as time changes, it is possible that at some other time t star, the particle has gone over here. Now your ER hat is going to be along the radial direction over there, and the tangential vector ET hat is going to be over here. Now very clearly these are unit vectors. That means their magnitudes have not changed. They still remain unit vectors. Their magnitude is 1, but their directions have changed, right? Now that direction is a function of the theta that you have over here. So ER hat is going to be a function of theta, which in turn is a function of time, right? Similarly, this is a function of theta, which is a function of time that you have. So when you're going to take the derivatives, you're going to take the derivative of the unit vectors also. Whereas in that problem you might have your derivative of ijk equal to 0 with respect to that particular same reference frame. Here, even when you're taking the derivative with respect to the same reference frame, you will see that these quantities are functions of theta, and theta is a function of time, and therefore you would have the unit vectors. Their magnitudes don't change, but the direction is a function of time, and therefore time derivatives of any vector will involve a derivative of the unit vectors also, right? So the position vector, on the other hand, for this particle, can you say, just like we had in the general case, remember we had the position as, let's say, SI EI. Okay, that's confusing. Let me expand it out. So SX EX hat plus SY EY hat plus SZ EZ hat is what we had a particular position, or we could put it as R to make it over here. So generalizing this rectilinear motion to a more 3D motion, you would have Rx EX hat, Ry EY hat, and Rz EZ hat. And now if I wanted to find the velocity, let's say Vx, Vy and Vz, it would be very simple to just take the time derivative of the scalar measure numbers over here, because Ex hat, Ey hat and Ez hat are not going to be functions of time if the time derivative is to be taken in the same frame of reference. In other words, I'm expanding in a particular frame of reference and taking the time derivative also in the same frame of reference, then it's quite clear that I'm going to have no change in the direction, only the change in the magnitudes. But here I'm going to have change in the magnitudes as well. Now this is the position vector of any arbitrary point. Rx Ex hat, Ry Ey hat, Rz Ez hat. What is the position vector in the cylindrical coordinate system? The same position vector of the same material point. I'm using two different systems to work out the same. So in this case, your Ex hat is here, Ey hat is here, and Ez hat is coming out of the plane of the board, right? Come again? Yeah. So how would you write R of t? So I could write R of t in this case as the x measure, y measure, z measure, and the corresponding unit vectors. How do I write R of t in the polar coordinate system, including ER hat, E theta hat, EZ hat? Mm-hmm.
And then use R, like use the.
Okay, let's keep things simple. Let's say there is no z. Okay, it's a planar motion. Let's say so. I don't have this term over here. Okay, so I'm going just from an xy system over here to an r theta system over here, right? So I have this distance. If I take the magnitude of this r, I get r, and Yeah, so if I take the magnitude of this, I get r, and this is the angle theta, and for which also I need to specify the direction over here, right? So r and theta. But now I want to say, with respect to this origin, what is the position of this, which is what I was expressing here as rx ex hat plus ry ey hat, right? Now how will I express it in terms of these quantities that I have introduced, the unit vectors er hat and et hat?
You go the r hat to the radial position, and then the theta hat is the degrees counterclockwise or clockwise you need to take to get to that point.
So are you using the and the R hat as
You're changing your reference frame to the ERET.
Uh-huh.
Right?
No, the reference frame, again, let me clarify, these are two different quantities, the frame of reference and the coordinate system, right? So I'm keeping the coordinate system the same,
Okay.
right? I'm sorry, yeah, I'm keeping the frame of reference the same. I'm only changing the coordinate system. I'm going from the Cartesian coordinates to the polar coordinates.
R cosine and R sine.
Good, but is it at all necessary?
Oh.
See, all that I want is the
All you need
position of this.
Yeah.
How do I get to there? I need a certain distance, I need a certain direction, right? To get from, all I need to get is from point O to point P, right? So what I'm writing over here is also R from O to P, right? Now here also I want from R from O to P. How do I get there? Here I had to do two parts. I had to go a certain distance along the x-axis multiplied by ex hat, and then I had to go a certain distance along the y-axis in order to reach the point and multiply that distance by ey hat. But to go from here to here in this system, all that I need to do is just to go on this line. I reach the point already. So what Atharva was telling was right, but only his first sentence was enough. All that he described after that was unnecessary because you already reached that point. So your r over here will just be the magnitude of that r, whatever distance you have gone over there, multiplied by your er hat. There's no et theta hat component. So even though you have introduced this et hat or e theta hat, you're not actually utilizing it as far as the position is concerned. But it will become
So what's actually the unit vector? There is none?
er hat. This is the unit vector.
But the unit vector is a function of theta, so it has direction.
Exactly. So
Oh, okay.
yeah, the point. Yeah. So in other words, your r is a function of, yes, magnitude as well as the direction, but just that this is contained within your unit vector. So it looks much more compact. Even when you go to 3D and extend this polar coordinate system to cylindrical, you'll just add another term, which is easy. So you'll have only two terms. Unlike here, you would have three terms with ex, ey, and ez. So it will be much simpler. But there, your ex, ey, and ez were not functions of x, y, z in general, but here they are functions of your theta. So when you're taking derivatives, you have to make sure that you take derivatives of both the quantities. So that's essentially what it's going to be. So some of your homeworks are based on that. So try explore that. I wouldn't mind if you have any issues, get stuck up with that because of this new complication. But we will, as you present in the next class, we will see where you're getting stuck up, what is the issue, what is the nuances involved for the polar or cylindrical coordinate system as opposed to your Cartesian coordinate system, and then it will become very easy for us to extend to the spherical coordinate system as well as the natural coordinate system, which involves the normal, tangential, and the binormal. So all of that we already introduced in term conceptually, but we will get into the equations once you make the presentations on the homeworks. Yeah. Thank you.